Okay, just check whether the screen is visible.
Yes, sir.
Okay, so let us start the physics session. So this was the last problem that we have discussed in the last session. Okay, so let us see the next problem. So in this problem, the question is the potential energy of a molecule on the surface of the liquid compared to that of the molecule inside the liquid. Whether the potential energy is smaller, the same, greater, and the zero. Okay. So if you consider this is the vessel, then if this is the free surface of the liquid, okay, then the potential energy of any molecule which is on the free surface, it is always greater than the molecule inside the liquid. Okay, so the correct answer is greater. So potential energy on the free surface, it is always greater than the potential energy for the molecule inside the liquid. Okay, see the next question. The surface tension of a liquid is a capital T. The increase in its surface energy on increasing the surface area by A. Okay. So this is the straightforward question on the equation of the surface tension. So we know the equation for the surface tension. This T is equal to, this is the surface energy per unit area. Okay. So from this we get the surface energy. This is equal to T into the area. So if we increase the surface area by the value capital A, then the energy stored or the energy increases. This is equal to surface tension into the area. Okay. So the correct answer is option B. So basically this problem is based on the basic equation W is equal to T into dA or T into A. Okay. Now let us see the next problem. This is on the soap bubble. So the problem statement given: the work done in blowing a soap bubble of the radius 5 centimeter is. So basically here we want to find out the work done to blow the soap bubble of the radius 5 centimeter, and the surface tension of the soap solution is given. This is 30 into 10 to the power minus 2 Newton per meter. Okay. So for the soap bubble, as we know, the soap bubble has two surfaces. One is the inner surface and second is the outer surface. Okay. So we have to consider the two surface area for the soap bubble. So the basic equation for the work done or the surface energy W is equal to the surface tension into the dA. Okay. So here dA will be 2 times, as we know, the for sphere the surface area is 4 pi r square. Okay. So just we have to consider two surface area. So T is given. So here T is 30 10 to the power minus 2. So this is 30 into 10 to the power minus 2. This is the surface tension into 2 into 4 pi and r square. So radius of this soap bubble is 5 centimeter. So 5 into 10 to the power minus 2. This is a meter square. Okay. Now just simplify this equation. So this is equal to 30 into 10 to the power minus 2 into 2 into 4 pi into, this is 25 into 10 to the power minus 4. Okay. So here this 30 into 2, this will be 60 into this 10 to the power minus 2, 10 to the power minus 4, this is 10 to the power minus 6, this 25 into 4, so this is 100, this is 100 pi. Okay. So we get 60 into 100 pi into 10 to the power minus 6. Okay. So you can put the value of pi as a 3.14. So this is into 3.14. Okay. Now this 100 means 10 to the power 2, and this is 10 to the power minus 6. So we will get W is equal to 60 into 3.14 into 10 to the power minus 4. Okay. Now just multiply this. So you can either multiply by 60 or just multiply by 6. So 3 into 4, 3.14 into 6. Okay. So this value will be 1884. So this is 18.84. Okay. So this is 18.84 into 10, as we have just multiplied by 6 into 10 to the power minus 4. So this is 18.84 10 to the power minus 3. Okay, so if I shift this decimal place on the left side, so it will be 1.884 10 to the power minus 2. Okay, so if you see the answer, the correct option is option B. So to solve the problem on the soap bubble, the basic equation that you should know, this is about the work done or the surface energy, W is equal to T into dA. Next, we should know the formula of the surface area of the soap bubble. So always remember, for soap bubble, it has two surfaces. So just multiply by 2. For sphere, the surface area is 4 pi r square. Okay. See the next question. A spherical liquid drop of radius capital R is divided into 8 equal droplets. If the surface tension is T, then the work done in the process will be. Okay. So basically here we have to find out the work done when the bigger drop is converted into smaller droplet. Okay. So this drop has the radius capital R. Okay. So it is divided into 8 number of droplets. So here n is equal to 8, okay, having the equal radius. So what is the work done? So there is a direct formula when bigger drop is converted into smaller droplet. So W is equal to 4 pi r square into surface tension T in bracket n raised to 1 by 3 minus 1. Okay, so this is the work done in the process when we convert the bigger drop into smaller droplet. Okay, so here r is the radius of the bigger drop, n is the number of droplets formed after the conversion. Okay, so as we know n is equal to 8, so we get 4 pi r square, the capital T, n is 8 raised to 1 by 3 minus 1. Okay, so basically here we should take the cube root of 8, that is equal to 2. So W is equal to 4 pi r square capital T, this is 2 minus 1, so finally this is 1. Okay, so 4 pi r square into capital T. Okay, so if you refer the answer, the correct option is option C. It is a 4 pi r square into T. So this is the correct option. Okay, so here formula we have used W when bigger droplet is converted into smaller droplets. Okay, so you should remember this formula, 4 pi r square capital T in bracket n cube n raised to 1 by 3 minus 1. Okay, refer the next problem. So this is on the soap bubble. So the work done in blowing a soap bubble. So the work done in blowing the bubble of radius r is W. Okay. The work done in making the bubble of the radius 2r from the same soap solution. Okay. So basically here we want to find out the ratio of initial work to the final work. So initial work, let us assume W1. Here we want the soap bubble having the radius r. So to make the soap bubble of radius r, what is the work done? So this is given by, this is 2. So basic formula is W is equal to T into the area. Okay. So T into surface area for the soap bubble, it is 2 times 4 pi r square. Okay. So here we get 8 pi r square into T. So this is the initial work done. Okay. Now from the same soap solution, if you want to form a soap bubble like this that has the radius double of the initial bubble, so it is a 2r. Okay. So the new work done W2, again we can write by the same formula, T into area. So T is same, just area will change. So 2 into 4 pi. Now here radius is 2r. So it is a 4 pi r square. So here we will get T into, this is 8 pi into 2 square will be 4, r will be r square. So this is 8 into 4, 32. So 32 pi r square into the surface tension T. Okay, so this is the new work done to form the soap bubble of the double radius. Okay, so the question is, the work done in making the bubble of radius 2r from the same solution is, so the new work done upon initial work done, this is equal to, this is 32 pi r square into T divided by 8 pi r square into T. Okay, so this is same. So 8 4 is 32. So W2 is equal to 4 into W1. So this is the relation. Okay, so you can see the answer. So the correct answer is option C. Okay, so here W is equal to 4 into W. So answer is option C. So this problem basically it depends on the equation W is equal to T into area. Okay, and here area for the soap bubble is 2 times surface area. Okay, now refer the second question. Okay, for the answer you can note down or you can directly take the screenshot. Okay, see the next question. Here 1000 small water droplet of equal size combine to form a bigger drop. The ratio of final surface energy to the initial surface energy is, okay. So what is given? We have the 1000 smaller droplet like this. Okay. So here what we have, n is equal to 1000. So it is converted into the one bigger drop like this. Okay. So what is the work done? So what is the ratio of surface energy, that is a new surface energy, to the initial surface energy? So this is the final surface energy. Let us assume this as a EF, and this is the initial surface energy. So it is a EI. Okay. So there is one straightforward formula. The ratio of final surface energy upon the initial surface energy, this is equal to 1 upon n raised to 1 by 3. So here n is given 1000. So this is 1 divided by 1000 raised to 1 by 3. So it is the cube root of 1000. So that is equal to 10. So it is 1 by 10. Okay. So the ratio EF as to EI, final surface energy to the initial surface energy, this is equal to 1 as to 10. So correct option is option B. So basically this formula, it is based on the equation of the work done or the surface energy. So if I consider the initial surface energy EI, okay, we have n number of droplets, okay. So here formula will be T into area. So T into area of n droplets, n into each droplet has an area 4 pi r square. So this is the initial surface energy, okay. Now all these droplets are converted into single drop, then final surface energy will be, for bigger drop, EF is equal to 4 pi r square. So this is the surface area into T, okay. Now here we have to find out what is the relation between the capital R and the small r. So for that we will use the equation for volume. So volume will remain same, final volume and the initial volume. So final volume will be 4 by 3 pi r cube, and initial volume will be n into volume of small drop 4 by 3 pi r cube, okay. So from this we will get the relation r cube is equal to, you can cancel out this, it is n into r cube, okay. And if you put this value in this equation, and if you take the ratio of EF upon EI, so finally you will get this relation, okay. So the basic formula will remain same, it is the work done or the surface energy, this is T into area, okay. Okay, so the problem that we have solved, they are basically on the surface tension and the surface energy. Now the next concept in the chapter 2 is the angle of contact. So basically angle of contact, it is nothing but the angle between the tangent drawn to the free surface of the liquid and the surface of the solid, okay. So this angle, this is the tangent drawn to the free surface of the liquid, okay, and this is the surface of the solid. So this angle will be the angle of contact. So we should know some relation for the angle of contact for different liquids, okay. So first we have the liquid having the concave meniscus. So for the concave meniscus, the angle of contact will be the acute angle. So angle less than 90 degree. So theta less than 90 degree. So this is possible for the liquid that partially wets the solid surface, okay. So here the example will be water. So water will have the acute angle for contact, theta is less than 90 degree. Second is the convex meniscus. So angle will be the obtuse angle. So theta will be greater than 90 degree. Okay. So when theta is greater than 90 degree, here liquid does not wet the solid surface. Okay. So this condition is possible if the cohesive forces of the liquid are greater than the adhesive forces. Okay. And the example for the convex meniscus or the obtuse angle of contact, it is the contact between glass and mercury. Okay. Now these are some vector relation for different angle of contact. So there can be a question on the angle of contact and the resultant vectors. So first we have the acute angle of contact. When there is an acute angle, that is theta less than 90 degree, then here the adhesive force AP bar. So AP bar means it is the adhesive force. It should be greater than AC upon root 2. AC is the vector for cohesive forces. So AC upon root 2. So AP bar will be greater than AC upon root 2. Second, if the angle theta is greater than 90 degree, that is obtuse angle, then the relation between the force is AP bar, that is the adhesive force, is less than AC upon root 2. Then for the hypothetical condition where angle of contact become exactly 90 degree, in that case, the adhesive force AP bar is exactly equal to AC upon root 2. Then for the liquid that completely weights the solid surface, theta will be 0, that is angle of contact is 0. In this case, the cohesive force vector is 0 and adhesive force AP bar is exactly equal to the AR bar. Then the next concept is the shape of the liquid droplet on the solid surface. Okay. So here T1, if you see this diagram, then there are three forces. One is a T1, then second is the T2, and third force is the T3. Okay. So the shape of the water droplet or any droplet, it will depend on three forces T1, T2 and T3. Okay. So basically T1, it is nothing but the surface tension at liquid solid interface. T2 is the surface tension at air solid interface. T3 is the surface tension at liquid air interface. Okay. So for equilibrium of any drop, this is the relation. So the relation is T2, it is equal to T1 plus T3 into cos theta, or cos theta is equal to T2 minus T1 divided by T3. So if the drop form acute angle of contact, then the T2 will be greater than T1 and T2 minus T1 will be less than T3. Okay. So in this case, cos theta is positive and theta will be the acute angle. It means example is water on glass. Okay. So in case of water on the glass, the angle of contact will be the acute angle. Second is the obtuse angle. So to obtain the obtuse angle, T2 should be less than T1 and T1 minus T2 will be less than T3. In this case, cos theta is negative and theta will be the obtuse angle. So example is mercury on the glass, and if T2 minus T1 is greater than T3, then cos theta will be greater than 1, which is the impossible. So in this case, drop will not form on the solid surface and the liquid will just spread over the surface. Okay. So there can be a question on these relations of T2, T1 and T3. So just you can take this screenshot. This is already given in your book. Okay. Then this is the theoretical part. The different factor affecting the angle of contact. And second factor affecting the surface tension. Okay. So you can read this from the textbook. Okay. Now the next concept or the formula, it is based on pressure inside a drop and pressure inside the bubble. Okay. So when the liquid drop is formed, the pressure inside, it is given by the relation, it is a Pi minus P naught. This is equal to 2T upon R. Okay. This is also called as the Laplace law of spherical membrane. So Pi is the pressure, P naught is the atmospheric pressure. This is equal to 2T upon R. Or simply we can write P is equal to 2T upon R. So this is for the drop. And for the soap bubble, the pressure will be Pi minus P naught is equal to 4T upon R. So basically this equation that we write, this is called as a gauge pressure. Pressure without considering the atmospheric pressure. Okay. And when we write this Pi minus, so Pi minus P naught, so this is basically a gauge pressure by removing the atmospheric pressure. Okay, so you should remember these two equations. This is for the soap bubble So basically it is for the hollow sphere and this is for the drop. Next concept is the capillary action. So for the capillary action, for capillary rise or capillary fall, the relation is H is equal to 2t cos theta upon R into rho into G. Okay. So here for capillary fall, in case of mercury, okay, you can observe the theta is obtuse. So cos theta will be negative. Okay. And for the capillary rise, theta is the acute angle. So here you can observe in the diagram when we can get the capillary rise. When there is a water, it is in contact with the glass tube, then we can observe the capillary rise. In that case, the angle will be theta, which is acute angle. And when there is a mercury inside the glass tube, you can see there is a fall in the mercury. Okay, so the angle of contact or cos theta is negative, so theta will be the obtuse angle. So the formula to be remembered is for the H. Okay, now let us solve the problem. So the first question given here is the meniscus of the liquid is a concave if P1 and P2 are the pressure just above and below the meniscus, then what is the relation? Okay, so this concept is given in your book with this diagram. So this is the diagram, this is the free surface, and this is the liquid. Okay, so the pressure just above the meniscus, if the meniscus is concave, so this is the concave meniscus. So let us assume this pressure as a P1 and this pressure is a P2. Okay, so pressure above the concave meniscus P1, it is always greater than the pressure below the meniscus. So P1 is greater than P2. Okay, so correct option here is the option B. Okay, refer the second question. The excess of pressure inside the liquid drop of the radius r and the surface tension T. Okay, so basically the question is about the pressure inside the drop. So we have to find out this pressure for the drop. So we have the standard relation, the Pi minus P naught. This is equal to 2T upon R. Okay, so this is for the liquid drop. So correct option is option B. And the excess pressure inside the soap bubble of the radius r and the surface tension T. So for the soap bubble, the relation for the pressure is Pi minus P naught. This is equal to 4T upon R. Okay, so the answer is 4T upon R. That is the option D. Okay, so these two questions, they are directly based on the formula of drop and the soap bubble. Okay, now ready for the next question. A capillary tube of the radius r can support a liquid of the weight 6.28 10 to the power minus 4 Newton. If the surface tension of the liquid is 5 into 10 to the power minus 2 Newton per meter, the radius of the capillary tube must be. So basically this problem, it is based on the equation of the surface tension. So what is given? There is a capillary tube like this. This capillary tube, it has a liquid. So this is the liquid inside the tube. This is the complete liquid. Okay. So this liquid will have certain weight. So this weight will act in the downward direction. So this weight is given, which is a 6.28 into 10 to the power minus 4 Newton. Okay. If the surface tension of the liquid is T, the radius of the capillary tube must be. So here we have to find out what is the radius of the capillary tube. Okay. So here what will happen, the complete weight of the liquid, it is supported by the surface tension, and this surface tension force, it will act on the circumference like this. Okay. So if you consider this is one ring, then this is the force due to surface tension that is acting on the circumference. Okay. So this force, it will support the weight. So if I write the equation, surface tension, this is equal to force per unit length. Okay. So surface tension is given, which is equal to 5 into 10 to the power minus 2 Newton per meter. This is equal to this force. This must be equal to the weight supported, that is the weight of the liquid. Okay. So just I can replace this as a weight divided by what is the length. Length means this total length which is in contact with the glass. Okay. So this length is nothing but the circumference, so that is equal to 2 pi r. Okay. So this is equal to w is given, so that is equal to 6.28 10 to the power minus 4 divided by 2 pi. So 2 pi directly I can write this as 6.28. So this is 3.14 into 2. So you will get the answer 6.28. Okay. Into radius is r. So this 6.28, this 6.28 we can cancel out. And then radius is equal to 10 to the power minus 4 divided by 5 into 10 to the power minus 2. Okay. So 1 by 5, this is equal to zero point 0.2 into 10 to the power minus 4 upon minus 2, this is minus 2. Okay. So if I write this as 2, then it will be 2 into 10 to the power minus 1 into minus 2. So if you add this, your answer will be 2 into 10 to the power minus 3. Okay, so this is the radius. So if you refer the answer, the correct option is option D. It is 2 into 10 to the power minus 3 meter. Okay. So the equation that we have used, it is the surface tension, force per unit length. Okay. Then the force value, this is nothing but the weight of the liquid supported by the glass tube or because of surface tension. Okay. And L is the circumference. So to solve the problem, we should know this basic or schematic diagram. Okay, now refer the next problem. So here 5 gram of water rises in the bore of capillary tube when it is deep in the water. If the radius of the bore of capillary tube is doubled, the mass of the water that rises in the capillary tube above the outside water level is. Okay. So basically here we want to find out the relation for the mass when we increase the radius and the initial radius. So just consider this is the initial glass tube and it is inserted in the liquid. Okay, and this is the water that rises in the glass tube. Okay, so suppose this height is a h1 for initial condition when the radius is suppose r. Now just imagine we double the radius. Okay, like this. So when we double the radius, so this is the rise of liquid. So let us assume this rise is a H2. Okay, so we cannot say H1 is equal to H2. Here the radius is basically 2r. Okay, for second condition. So here we want to find out the mass for initial condition. Let us take this mass is a m1. Okay, for the liquid which is in the tube. For second condition, the mass is m2. Okay, so here we have to find out the m2. What is the mass in the second case? M1 is given. For first case, M1 is 5 gram. Okay. So to solve this problem, we should know the relation for the rise of the liquid. So H is equal to 2t cos of theta upon rho rg. Okay. And here mass of the liquid which is inside the tube, this is equal to, so mass is definitely, it is volume into density. Okay, density is mass upon volume. So what is the volume? So volume will be the cross sectional area A1 into the height H1. Okay, so this will be a cylinder for the liquid inside the tube. Okay, so this cross section is A and this height is H. The volume will be A into H. So similarly here, for the first case I can write initial mass M1, it is equal to area A1 into the height is H1. Okay, into density rho. So A1 is pi r square. What is H1? This formula. So it is 2t cos of theta upon rho rg into the density. Okay. So just we can cancel out this r with the r square. So what we get as m1, this is pi r into 2t cos of theta, and we can cancel out this rho. Okay. So just remaining value is g. So consider this equation 1. For the second tube, the mass will be m2, area will be the cross section A2, sorry, volume will be A2 into H2 into density. Okay, what is A2 here? It is pi, radius is equal to 2r, so it is pi r square, 2r square into H2 is 2t cos theta upon rho. R means radius, so it is a 2r into g into rho. Okay, so can, rho will get cancelled. So this will be 4r square. So pi into 4r square into 2t cos of theta upon, this is 2r into g. So this 2, this will be 2 r square. So the remaining value is pi. So this is 2 pi into r into 2t cos of theta upon g. So this is equal to 4 pi r cos theta upon g. Okay, now this is the equation 2. Now if you take the ratio of m2, that is equation 2 divided by equation 1, so if I write m2 upon m1, okay, so finally you will get the ratio as, remaining all the values are same, so you can cancel out pi r with the pi r, this t cos theta g, this t cos theta g. Okay, so just 4 divided by 2, so this ratio is 2. So m2 is equal to 2 into m1. So m1 is given 5, so m2 is equal to 10 gram. So correct option is option C. Okay, so to solve this problem, the basic equation that you should know, So it is about the height h. Okay, so this is 2t cos theta upon rho rg. Second equation you should know about the volume inside the glass tube. So volume is cross section area A into the height of the liquid. Okay, that is the h. And next formula is about the density. This is the mass upon volume. So mass is equal to density times volume. Okay, so you can take this screenshot. Okay, now refer the next problem. So two capillary tubes of the same material but of the different radii are deep in the liquid. The height to which the liquid rises in the two tube are 2.2 centimeter and 6.6 centimeter. The ratio of radii of the tube is, okay. So we have to find out the ratio of their radii. So two capillary tubes. So this is the first tube that has a radius r1. This is the second tube that has a radius r2. So they are deep in some liquid. Okay. So in the first glass tube, this is the rise of the liquid. So let us assume this height as a h1. In the second tube, this is the rise of the liquid. So let us assume this as a h2. Okay. So we have to find out the ratio of their radii. So here h1 is given. So rise of the liquid in the first glass tube is 2.2 centimeter. H2 is given, that is equal to 6.6 centimeter. So these two heights are given. So what is the ratio of their radii? Okay. So we should know the relation for H. This is equal to 2t cos of theta upon rho rg. If everything is constant for both the glass tube, so both have same material, then same liquid. Okay, so the tension T, density rho, then cos theta or theta, they will remain same. Okay, so therefore h is proportional to the radius, so and it is inversely proportional. So we can write h1 is proportional to r1, h2 is proportional to r2, and if you take the ratio h1 upon h2, so this is equal to, this will be 1 upon r1 upon 1 upon r2, so that will be r2 upon r1. Okay, so h1 upon h2, these values are given. So this is 2.2 upon 6.6. So this is equal to r2 upon r1. Okay, so from this r2 upon r1 is equal to 1 upon 3. Okay, so here the ratio, this is for r2 upon r1, and the ratio that we need is r1 upon r2. So it is 1 upon 3. Okay, so the correct answer, sorry, this is 3 upon 1. Just we have to take the inverse. So r1 upon r2, it is 3 as to 1. So the correct option is option D. Okay. So to solve this problem, the basic equation that we have used is for the h, and we know that height of the liquid in the glass tube is inversely proportional to the radius of the glass tube. Okay. From that you can write these two relation h1 and h2, and then take the ratio h1 upon h2. So this is equal to r2 upon r1, and we need the ratio r1 upon r2. So just take the inverse. So it is 3 as to 1. Okay, and the last concept in the chapter 2 is about the fluid motion. So in the fluid motion, first we have the flow visualization methods. So in that, the flow line, then streamline, then laminar flow, and the turbulent flow. Okay, So just you can read this from the textbook. Just I have given the definition. If you want, you can take the screenshot. Okay, next there is a formula for the critical velocity and the Reynolds number. So the critical velocity means the velocity beyond which the streamline or the laminar flow it becomes the turbulent. So that velocity is called as a critical velocity. So critical velocity it is given by the equation Vc is equal to the Reynolds number Re neta, that is the viscosity, upon rho d. Okay, sometimes the symbol for the viscosity it is given as a mu, so it will be Re mu upon rho d. Okay, and from this we can write the Reynolds number as Re is equal to, so it is rho v into d. V is a Vc upon the viscosity nu. Okay, so this viscosity basically it is the dynamic viscosity. So there is a relation for laminar flow, turbulent flow, and the transition flow. So if Reynolds number is less than 1000, the flow is called as a laminar flow. If the Reynolds number is greater than 2000, flow becomes turbulent. Okay, the meaning of laminar flow is, if you consider this is the pipe and there is some fluid that passes through the pipe, then all the fluid particles will move in a single line. Okay, so there is no mixing of the particle from one layer to the other layer. So this is called as a laminar flow. The turbulent flow means the particle from one layer will mix into the other layer. So suppose this is the initial flow, which is the perfectly laminar. Then after some time, you can see the flow like this. So this type of flow, where the particles from one layer mixes into the other layer, this is called as a turbulence. Okay, so mathematically the turbulent it is given by this relation. The Reynolds number for turbulent flow, sorry, this is not the turbulent flow. Reynolds number for turbulent flow is greater than 2000. And if the Reynolds number lies between 1000 and 2000, the flow is called as a transition. Okay, so the relation that you should know first is the critical velocity, second relation is the Reynolds number, and Reynolds number is given by the ratio of inertia force upon the viscous force. Okay, now next concept is about the viscosity. So basically viscosity it is the property of fluid due to which the one layer of the fluid offers a resistance to the motion of the adjacent layer. Okay, this is also called as a fluid friction. So for the viscosity there is a relation or the law that is called as a Newton's law of viscosity. So Newton's law of viscosity, the basic equation is the shear stress offered by the fluid, this is equal to viscosity mu into ratio du by dy. This is called as a velocity gradient. Okay, and this tau is nothing but the force per unit area. So this is the shear force. This is equal to mu into, sometimes u can be given as a dv upon dy. So mu or neta both are same. These are the viscosities. So you should remember this equation: F upon A is equal to mu into dV by dy, or F is equal to mu into area into dV by dy. Okay, because of the viscosity, suppose this is the ground or the stationary surface. This is the liquid that flows above that fixed surface. Then because of viscosity, we can see the velocity variation. The topmost layer or the free surface will have the maximum velocity, and this velocity it will go on reducing like this. So this variation, if I consider this direction as a y direction, okay, so this variation of velocity, this is given by the equation, it is a dv upon dy. Okay, so this is called as a velocity gradient. So for the viscosity or Newton's law of viscosity, we should remember the equation tau is equal to mu into du by dy or dv by dy. Then tau is force upon area, and from this we can write force is equal to mu into area into dv by dy. Okay, now there are some unit conversion for the dynamic viscosity. So the SI unit for the viscosity mu, this is Newton second per meter square, or Newton per meter square is nothing but the Pascal, so it is a Pascal second. Okay. Now CGS unit for the viscosity, it is a poise. So poise is nothing but dyne second per centimeter square. So one poise, this is equal to 1 by 10 or zero point 0.1 Newton second per meter square. And the second viscosity is the kinematic viscosity. So kinematic viscosity means if you divide the dynamic viscosity by the rho, okay, it will become the kinematic viscosity. So you should remember this equation for the kinematic viscosity. It is the mu divided by the density. Now, depending on the viscosity concept, there is one law which is called as a Stokes law. Okay, so Stokes law, it gives the relation for the force acting on the sphere or the drop that moves through the viscous fluid. So F is equal to, suppose this is the sphere and it is freely falling in some viscous fluid. You can consider as oil. Okay, then it will offer some force because of the viscosity. So that force is given by the relation F is equal to K into viscosity neta or mu into R into V. Okay. So for the spherical object, the K value, this is equal to 6 pi. So relation for the force for the sphere, it is a 6 pi into viscosity into radius into the velocity. Next concept is about the terminal velocity. So terminal velocity, it is given by the relation V is equal to 2 by 9 r square in the bracket rho minus sigma upon eta into g. Okay. So there can be a question directly on the terminal velocity, that is to find out the terminal velocity. Then you can use this relation. Okay, so let us solve some problem on the viscosity. Okay, now this first question, it is about the type of flow. So flow given is a laminar flow. Then for the laminar flow, the velocity of the flow at any point in the liquid. So it does not vary with time, may vary in the magnitude but not in the direction, may vary in the direction but not in the magnitude, may vary both in magnitude and direction. So for the laminar flow, the velocity does not vary with time. Okay. So correct option is option A. Like for the second question, which of the following is not the property of the laminar flow? So first option is flow may be along the curved path. Velocity of the flow is independent of time. Velocity of the flow may be different at different points. Liquid molecule may cross from one layer into other layer. Okay, so which is not the property, so that is which is not the correct statement. So last is not the correct statement for the laminar flow. So option here is option D. Liquid molecules may cross from one layer to into other layer. So for laminar flow, all the particles will remain in a single layer. Okay, there is no mixing. So option here is option D. Okay, now this question is based on the viscosity. With rise of the temperature, the viscosity of the gas. So as we increase the temperature, the viscosity will go on reducing. So the correct option is option B. The viscosity will decrease. Next question is about the for ideal fluid. So you should know some properties for the ideal fluid. The viscosity of the ideal fluid. So ideal fluid viscosity is always zero. So ideal fluid is referred as a inviscid. So meaning of inviscid is it doesn't have any viscosity. So correct option is option A, viscosity is zero. Refer the third question. The angle between the viscous force and the motion of the flow of liquid. So if you consider this is the pipe and there is a liquid that flows through the pipe. So this is the liquid flowing in this direction. Okay. So viscous force is always in the opposite direction. So viscosity basically try to oppose the motion. Okay. So this is the direction and this is the viscous force. So the angle is viscous force and this is the direction. So this angle is 180-degree, that is equal to pi radian. Okay. So correct option is option D. Angle is pi radian. Okay, ready for the next question. The velocity of the water in the river is a 9 kilometer per hour for the upper surface. So the schematic diagram is like this. This is the ground, okay, and there is a liquid in the river. So velocity of this upper surface is given. This is completely the water. At this surface, the velocity this is given as this is 9 kilometer per hour. Okay, the river is 10-meter deep, so depth is 10 meter. If the coefficient of viscosity, so mu, this is given as a 10 to the power minus 2 poise, okay, then the shearing stress. So we have to find out the shearing stress. So basically this problem, it is on the Newton's law of viscosity. So the equation that you should know to solve the problem. So here shear stress is equal to mu, that is viscosity, into the velocity gradient dv by dy. Okay. So here mu is given 10 to the power minus 2 poise. So we have to convert this into SI unit. So we know 1 poise, this is equal to zero point 0.1 Newton second per meter square. Okay. So just multiply this by 0.1. So 10 to the power minus 2 into 0.1. This is Newton second per meter square. So zero point 0.1 means 10 to the power minus 1. So mu is 10 to the power minus 3 Newton second per meter square. So this is the value of mu. Okay. Now what is dv by dy? So this dv by dy is nothing but the velocity gradient. So you can observe here at the topmost layer velocity is 9 kmph. This is the height and this is the velocity gradient. Okay. So here dv is nothing but 9 minus 0 and dy this is equal to 10 meter. So 9 minus 0, this is 9 kmph, kilometer per hour. So first we have to convert this into meter per second. So there is a relation for kilometer per hour and meter per second. So to get the meter per second, for kilometer per hour multiply directly by 5 by 18. So answer will be in meter per second. Okay. So 9 into 5 by 18. So this is 2. So it is a 5 by 2, that is equal to 2.5. Okay. So your dv value is 2.5. So now refer direct the equation tau. Mu is 10 to the power minus 3. dv is 2.5. This is in SI unit, so this is meter per second. And dy is a 10 meter. Okay. So 10 to the power minus 3. This is a minus 2 into 2.5. So your answer is, so just we have to shift this decimal place. So there is no answer given in 2.5. So write this as a 0.25. So 0.25 means 10 to the power, this is 10 to the power minus 10 to the power 1. So this will be, so this is 10 to the power minus 2 into 2.5. Okay, just check the calculation mistake. So we should get the answer 0.25 10 to the power minus 3. This is the correct option. So somewhere we are missing the power. So it should be minus 3. Okay, so try to complete this. The final answer is 0.25 10 to the power minus 3. The procedure is correct. So the first formula is mu is equal, tau is equal to mu into dv by dy. Okay. Convert this mu, which is given in poise, in terms of Newton second per meter square. Okay. So zero point 0.1 means 10 to the minus 1. So minus 3. Okay. So today we will stop here. Remaining problem we will solve in the next class. Just you can take the screenshot and try to solve.